seminar. And this time we have Sanford is a postdoc at the Caltech right now. He has been doing a lot of research on dark matter and SUSY scenarios and special isospin violation. And today he is going to tell us something about the Higgs masses at the 3-loop order and neutrino dark matter at TeV scale supersymmetry. And let's welcome him.
Okay, thank you for having me. The title of my talk is kind of a mouthful. In fact, what I'm going to be talking about is the Higgs mass at 3-loop order, and then also neutrino dark matter. And they're only tangentially related in that I will be talking about sort of TeV scale SUSY in both cases. But these are sort of two different separate topics, and then I'll relate them at the end. And this is based on work done with Patrick Draper, Jonathan Feng, Philip Kant, and Stefano Profumo in 2 different papers earlier this year. Okay, so to give you an outline of what I'm going to be talking about, first I'll talk a little bit about the status of supersymmetry, sort of the required thing we talk about in all SUSY pheno talks, current results, and possible directions, and then motivate why I'm going to be talking about TeV scale SUSY. A lot of the buzzwords these days are about looking for ways to hide supersymmetry in various scenarios. I'm going to be motivating why I'm going to be talking about things basically above 1 TeV for most of the talk. Then I'll be talking about the Higgs mass and the MSSM. And first I'll put in some comments on the uncertainties in the 2-loop determinations, and then what is added by 3-loop contributions, and what that implies for a SUSY parameter space. And then finally I'll talk about focus point dark matter, implications of various searches, both direct searches and indirect searches for focus point SUSY. And finally, at the very end, what MH equals 125 GeV at 3 loops means in focus point SUSY, related to the dark matter results. Okay, so what's supersymmetry look like right now? Well, it's very stringently constrained by the LHC, with between 5 and 20 inverse femtobarns of data based upon the search. You can see this is a bunch of collected searches. This line here is 1 TeV, so you can see in many scenarios, and these are sort of the unified model scenarios, it's colored superpartners are restricted to be above about 1 TeV. And that's especially true if you say look at squarks and gluinos together, have them be about the same scale. You have constraints that are in some cases much larger than 1 TeV, up to 1.7 for a particular search in the CMSSM. And really that comes from the fact that we have very stringent bounds on gluinos. They're even in simplified models, sort of just a gluino decaying to a neutralino and some quarks. Really, you have a bound of about 1.1 to 1.4 TeV, and it's pretty robust. So we have very strong bounds on colored superpartners. And if you look in particular at everyone's favorite region to just use as an example, the CMSSM, you can see that the light region is very severely constrained, down below about 350, maybe up to about 450 now in M1/2, and below at least 1 TeV in M0. And this is at 5 inverse femtobarns. They don't even make these plots for 20 inverse femtobarns anymore. I'll talk a little bit about that later. But in any case, the conclusion these days is that if SUSY exists, it's either heavier than expected, or it's more complicated and harder to see than expected. Okay, so where do we go from here? Well, there are many gaps in SUSY analyses, and these have been looked at by various people present in the room. And I'll talk about a few of them. I feel a little bit awkward talking about what people here have done to them, but at the same time, I don't want to act as if nothing has been looked at in this front. So first, there's gaps in basically kinematics. Where, given the kinematics of the scenario, do we actually have weaker bounds? And the first thing that is obvious is non-zero LSP masses significantly weaken or nullify the bounds. So you have here a gluino neutralino simplified model search. It says the gluino should be above about 1.4 TeV, but if you have a neutralino of above 700 TeV, then you have basically no gluino bound. And similarly for squarks, a squark neutralino simplified model says that the squarks should be above about 800 GeV, but if the neutralino is greater than about 300 GeV, then there's no bound again. So you can significantly weaken all these LHC bounds by just raising the LSP mass. And also, even if you don't raise it above, say, 700 GeV for the gluino, there's also the possibility of degenerate spectra. So when you have the gluino decay to the neutralino, but the quarks that come off are sufficiently soft so that you can't see them, then you have much weaker bounds. So you can see a little bit of it here, very degenerate gluino and neutralino, weakens the bounds even for 600 GeV neutralinos. And here in the squarks, if you go down to 250 GeV, this gap actually keeps going down to lighter mass. So if the squark and the neutralino are within, say, 10 GeV, you really just can never see it, because the quark that's coming off the squark decay will never be hard enough for you to see the signal. So that's one way that you can hide SUSY at the LHC. You can also look at third generation of production. Most of these bounds are really only about first and second generation squarks. So if you look at third generation, the bounds are much weaker. This is various TT bar, this is various stop-stop production bounds. And you see that you only get up to somewhere between maybe 550 and 750 GeV, so it's a weaker bound than other squarks. And also there's this window open at around the top mass, where a stop can exist, and it would be very, very hard to see it. So that's one direction that a lot of people are looking at, because they feel that it's a lot more natural to have the stop around the top mass than up at a TV. And also it's a scenario that we should look for. We always want to constrain as many scenarios as possible. And then another thing that people here have looked at in particular is bounds on electron-weak production. So if you say, okay, well, maybe the colored superparticles are very heavy, we'll never be able to see them, they're 3 TeV, or we won't be able to see them soon, they're at 3 TeV, we can still have light leptons and light neutralinos and charginos. So this is electron-weak production, and you see that the bounds, even on sort of the best searches, are only up to about 600 GeV in the chargino mass, neutralino mass, and this depends upon there being light leptons. The red curve, the blue curve, and the pink curve depend upon light leptons. If you don't even have light leptons, if you just have light neutralinos and charginos, you have the gaugino-Higgsino sector be a lot lighter than than all the fermions. Then the strongest bounds are this green bound. So that really only constrains the neutralino to be above about 100 GeV, chargino to be above about 300 GeV. So these bounds are much weaker, and there's a lot of parameter space that can be covered. And particularly if you're interested in dark matter, you don't need any fermions you don't need any fermions, so you can have just light electroeugenos to be the dark matter. So that's an interesting scenario. There are various other gaps. You have R parity can hide signals, though it can also lead to stronger constraints in some cases. You have long-lived NLSPs with gravitinos or RPV, and that has different signals that people can look for. You can go beyond the MSM, things like rack gauginos, like pseudoscalars. Won't really talk about that, but these are all possibilities for having supersymmetry, but not seeing it in the current searches. And then just as something important that's not really theoretic, not really a pure theory thing, but important for the LHC searches, is having new kinematical variables to close these gaps more effectively. It's not really new searches so much as doing the current searches better. So these are all very interesting things to do, which I will talk about none for the rest of the talk. Instead, I'm going to be talking about SUSY that is heavy and possibly beyond the LHC reach, order 1 to 10 TeV. And this is normally not considered because of naturalness issues. It's seen as unnatural for all the superparticles to be above, or at least the squarks, and particularly the stops, to be above a TeV. But really, it has several advantageous points. It avoids issues with lack of signals across all searches. So you may see nothing in one search, but seeing nothing in all searches is sort of troublesome, at least on a psychological level. Heavy stops produce MH of 125 GeV, the observed Higgs mass, much more easily. The fine-tuning issues, I would argue, aren't as big as they're sometimes claimed to be, and you can suppress flavor and CP violation effects. Okay, so let me talk about this. I think that the biggest motivation really is the Higgs boson. So we observe, the experimentalists observe MH to be about 125 GeV. And that's very consistent with very low spread and low error at both Atlas and CMS. And this, in normal MSSM scenarios, requires either very heavy stops or very mixed stops. So you can see here's this standard CMSSM plane. 125 GeV Higgs is up here. 125.6 is sort of up at the very edge of the plot. It's sort of barely this little corner. So you need stops to be very heavy, much heavier than the current bounds, which are sort of down here. It's way beyond that. And that corresponds to M stop of about 79 TeV, and that's for zero mixing. You can make this better by going to a more mixed scenario. And in fact, the reason that the experimentalists don't make this particular plot anymore with tan beta 10 and A equals 0 is because you can never get anything. So they've gone to A equals much larger values in order to actually be able to plot the Higgs mass somewhere that can actually be probed by collider switches. But the issue is that it results in significant fine-tuning. Let's look at that. The typical weak scale fine-tuning measure that people look at is something like mz squared over m stop squared. So for up in this corner, that's generally about 0.01%. That's sort of the tagline. It varies depending upon what spectrum generator you use, what Higgs mass calculation you use. But that's sort of the general idea. It's about 0.01%. However, if you start looking at this in detail, some odd things start to happen. So if you take a fine-tuning measure that's based upon the fundamental parameters, say, of the CMSSM, and this is just a fairly standard fine-tuning measure, you get a little bit less fine-tuning. So this is this 2000 line is 0.05%. So it's a little bit better. And by playing around with the boundary conditions, having a different boundary condition at the gut scale can improve the fine-tuning a lot more. I don't want to go into this because it's a little technical and not terribly relevant, but maybe 2% to 10% based upon what you want to do. And this isn't really to motivate, well, it's perfectly natural to have stops at very heavy masses. It's more to illustrate that these fine-tuning measures are very fragile. If you start dissecting them, they're not parameter independent, they're not sort of philosophy independent, whether you do weak scale or you do gut scale or you try to do it in terms of some string model that gives you gut scale parameters. It's a very fragile way to think about things. What the real fine tuning is not really clear based upon just the statement that you need 7 TeV stops. It's unclear what's really going on. So it's still a motivating problem. It's still something that's a little unfortunate if you have stops at 7 TeV, but it's not necessarily a gigantic problem. Another issue with fine-tuning is that we talk a lot about the Higgs potential and how fine-tuned the Higgs potential is. However, what about the precision flavor and CP sector observables? There are many of these. You have various meson mass differences, meson mixings, decay asymmetries, rare decays, electron and neutron EDMs, and none of these show any really significant evidence of new physics. And the standard way of looking at these is to say, well, many are suppressed, not all of them necessarily, but many are suppressed by a new physics flavor sector that has some sort of flavor symmetry. GMSB is the classic SUSY one. And so maybe it's not a problem, maybe there really is new physics flavor stuff that prevents these from being violent. But they're also suppressed for large fermion masses. So you sort of have a balance between, okay, having large fermion masses increases fine-tuning in the Higgs sector, but it also decreases fine-tuning in a general flavor sector. And in particular, if you look at Edm constraints, you see that generically, soft masses have CP phases that don't necessarily have anything to do with the flavor behavior. And they are strongly constrained by EDM. So looking at one, which is a CP phase between the gaugino mass and U-term, which aren't really in a general theory related necessarily. There's no reason they necessarily have to have the same CP phase. You can look at a CP phase in an almost CMSSM scenario, just add this. and look at what the constraint on the EDM's place on that phase is, and you see that it's fairly meaningful even for multi-TeV scalars. So up to about scalar masses of 4 TeV, so for the lightest M1/2 available, you still have a constraint from the electron EDM that the space has to be, sign of the space has to be less than 0.1. So you still have some amount of fine-tuning that has to be done. For even lighter things, down here has to be sort of 0.01% fine-tuning in this CP phase. So this is still a constraint, and this is still a constraint even in scenarios with MFB. So I'm not really advocating a strong fine-tuning measure, but there is an issue here with flavor and CP effects. How much do we tune those to get down to 200 GeV stops so that we can have a completely unfine-tuned Higgs sector? I think I just said most of this. And really, in addition, things like the CMSSM, we know that the CMSSM is flavor neutral, but that's really just an experimental thing because it's just too complicated to try to add in all these flavor phases, CP phases, and it doesn't really inform any of the collider phenomenology. And in particular, if we have light stops with heavy other squarks, that really introduces some flavor behavior, so we have to really worry about having a flavor sector reintroduced. So again, I'm not advocating any sort of like numerical fine-tuning measure, but it's something that also sort of motivates somewhat heavier SUSY scales. Okay, so motivation out of the way.
So are you going to mention, does the G-2 stuff come in here anywhere? Or the neutrino mixing and the possibility of what that could have to do with matter-antimatter asymmetries?
Neutrino mixing is completely constrained to this lepton sector. I'm not sure that necessarily has much to do with anything that I will be talking about. I'll be talking about mostly stuff that relates to stops and stuff that relates to dark matter, which doesn't necessarily relate to the lepton sector. G-2 in particular, you can easily have you can actually get the central value on G-2 with a, say, 600 GeV Muon and 800 GeV, 600 GeV is neutralino, 800 GeV Muon. You can get the central value of G-2 or pretty close to it, and it doesn't necessarily have anything to do with the squark sector. That's the trouble, is that G-2 is an issue, and it's something to keep in mind, but it's only really a strong issue if you really believe that the CMSSM says first and second generation squarks must be related to third generation squarks, leptons must be related to squarks, and the squarks must be related to the Higgs mass. There's several steps of unification in the CMSSM that are required to do that. And if you don't require those and can have a more general parameter space, you can very easily do G-2.
So in some sense, where you're going is you're trying to be talking about scenarios that are likely to produce observables at the LHC. In some sense.
Yeah.
And you're trying to stay close to those types of scenarios and stay further away from scenarios which would be non-observable.
Well, I'm going to be talking about both, but I'm more interested in things that will be, I will talk about things that are observable at the LHC, and I'm more interested in things that are observable in dark matter experiments.
Okay.
And I'll show what I mean later. Okay. Okay, so that out of, I will talk about things that are observable in dark matter here. This is a little bit more all the stuff that is an issue in calculating the Higgs mass and saying what that means for the SUSY parameter space, which is important either way. Okay, so the Higgs mass in the MSSM. I already said this, but let me reiterate. I think that the Higgs mass is the strongest numerical constraint on the MSSM parameter space, much stronger than fine-tuning. Fine-tuning is sort of a fairly fragile, sort of nebulous statement about where we believe SUSY should be. The Higgs mass, you need to have the SUSY input, and the SUSY parameters feed in very directly into the Higgs mass calculation. So it's a much stronger numerical constraint. And in particular, I think that, and this is not a popular thing to talk about, but having the SUSY masses below about 10 TeV, I think that's the Higgs mass is really the strongest motivation for that. If you're willing to go up to 10 TeV, then the Higgs mass I think is stronger than fine tuning to keep you below 10 TeV. And that's just because this is about the upper limit on what the stop masses can be and still give you a Higgs mass of 125 GeV. And at the same time, if you were to have M SUSY above 10 TeV, it would put you into a very special region of parameter space. And something to note is that experimental determination of MH is already much better than theoretical determination. It's already the error is already less than a GeV, which is amazing. And it's a year and a half in, and it's already less than a GeV after discovery, 2 years after the first signals were announced. Whereas the theoretical error is somewhere between about 3 and 5 GeV. And this is not the number that any particular code will claim. This is a tricky number, I will admit. This is not the number that any particular code will claim. Most of them will claim 1.5 to 2.5 GeV. This is an uncertainty, which I think is probably a more honest one, that is determined by a comparison of multiple codes back in 2004, but I don't know of a good update to it. And what it basically says is, okay, given all of our codes, given all of the different inputs, numerical inputs, all the different loop orders that we run things at, all of that, what is the spread in the results? And that's probably a more honest comparison because each code does things a little bit differently. And this is what they determined.
So that's more of a methodological uncertainty rather than an uncertainty by varying the values of your input SUSY.
Yeah, there's parametric uncertainty, and this is there's various other uncertainties, but they are real uncertainties. And I'll talk more about that. But this is really important because M SUSY is the MH is logarithmically dependent upon the SUSY masses. So the implications of this uncertainty are huge. And just to give a taste of that, if we take MH of 125 GeV, this is a little bit old slide, but it's illustrative, and the error of 3 to 5 GeV, plus or minus 3 gets you down to here and way up to here. Plus or minus 5 gets you way down to here, way up to here. That's sort of 1 sigma theory uncertainty. So that's a huge issue. 2 sigma would get you all the way down to 115 if it were really plus or minus 5 GeV is what we would have to add to all these determinations. And there are many sources of this. There's renormalization scheme dependent, so how you do the renormalization, is it MS bar, is it DR bar, is it do you use on-shell parameters, all this stuff. There's what scale you use, and this is basically uncertainty into higher order corrections. Zero and external momentum approximation in doing the Higgs potential. And these are all uncertainties, and then in addition to that, you have to add the experimental inputs. And I'm unclear whether, I think that's the parametric uncertainty at the time was folded into this. So this is also parametric uncertainty in M-top and alpha S. But all these sources of uncertainty feed into this, and they give a very large region of parameter space from maybe visible in 100 inverse femtobarns at the at 13 TeV LHC to never visible at any conceivable collider. And that's a giant uncertainty band. So this is a huge issue for whenever you stick a SUSY spectrum into a spectrum generator and get out a value for the Higgs mass. What do you do with that? What is the actual uncertainty that you add to that? And in addition, 3-loop effects are expected to be important and expected to be generically positive. So in addition to all of this uncertainty, you have sort of a feel that your true value, your true 125 GeV line should be somewhere a little bit lower. And where lower depends on how big 3-loop effects are. Okay, so before getting to 3-loop stuff, let me say a couple more things about the stop mass of 2 loops. At tree level, well, first at tree level, for anyone who's not familiar with SUSY, the Higgs mass is strictly lower than mz times parameter cosine beta. Not terribly important what beta is because in the limit that we care about most of the time, large tan beta, it's within 1 GeV of mz. So generally, the Higgs mass at tree level is about 1 GeV, is within about 1 GeV of mz. And then you need radiative corrections from the stop sector in order to raise the Higgs mass above the mz, so about 90 GeV. and it's very sensitive to both the stop mass and stop mixing. You have the minimal contribution for no mixing, and maximal contribution for the mixing angle at maximum contribution is completely mixed. But the size of the off-diagonal mixing term of root 6 m stop for equal m stop left and m stop right is the maximal contribution. And the general idea is that for the two-loop results, which is what all the current codes use, or all the standard codes use at least, two-loop at small mixing mass, you require about 5 to 10 TeV stop masses. The exact dependence, the reason that this is such a large band is because of the various parameter inputs. When we normalize the inputs in our analysis, we got that most of the two-loop result codes gave it between 6 and 7 TeV. So they are a much narrower band if you're careful to make sure that they have the same inputs. Those aren't the out-of-the-box inputs, though. Okay, so going towards what are the three-loop results? What are the three-loop contributions? Well, we used a program called H3M, which one of my collaborators, Bill Kant, put together. It was his thesis work. And it has 16,000 diagrams to various parts of the Higgs potential, and all of them are the leading order alpha t alpha s squared corrections. So this isn't all three-loop corrections. This isn't even all strong corrections. This is alpha t alpha s squared, which are the largest corrections by leading log analysis to the Higgs potential. It uses a standard. It doesn't calculate all the running and stuff by itself. It uses an input file from some other spectrum generator. We use Stochasticity 3.3.7. That's not really important. Just a note for what we use. But it doesn't do its own running. And the importance of that is that the parameters output by this are not high enough loop order for three-loop corrections. They're generally one loop in alpha s, one loop in mt. So you need a higher loop determinations of fundamental parameters to get an accurate Higgs mass. H3M does various runnings. It runs alpha s at 4-loop order in ms bar and does a transition to SQCD. It also runs MT at 4-loop in ms bar, does a transition to SQCD. You notice that these are at different loop orders, these transitions. All of this is because there is reliable code that does 4-loop ms bar calculations. There's reliable code that does these transitions. There's reliable code that does the 4-loop ms bar MT calculations, but it's a different code. So all of this is sort of strung together in finding other reliable codes that already have these runnings, that rather than try to code it ourselves, rather than try to code it ourselves and maybe get it wrong. So there's a lot of work that goes into getting all this right. And even on top of that, H3M just uses fine Higgs for 1 and 2 loop contributions, but it uses these higher loop order MT and alpha S contributions so that it gets the right order effects in. Looking at the effects of that, in particular in terms of renormalization scale, which I cited before as an important error, an important uncertainty issue, you see that the relative signs and contributions are very renormalization scale dependent. So if you say, okay, what renormalization scale are we evaluating MH at from 100 GeV up to 1 TeV, the one-loop corrections vary by about 8 GeV. So it's very important for what the one-loop corrections are at on the renormalization scale. It's a huge dependence. Two-loop is a little less dependent, but even here you see about a 1 GeV variation between the minimum value and the maximum value. And even more important, the relative sign, even the qualitative, does the two-loop result add or reduce the one-loop result? That's dependent upon the renormalization scale. So even the qualitative behavior of the different contributions is dependent upon this this number. 3-loop is even a little bit less renormalization scheme dependent. It's about half a GeV difference, but there's still some dependence. And all of these are really how much of higher order contributions are you folding in. There's no real right number here. You really have to go to higher order to say what is the best number. So for instance, knowing that this three-loop contribution is here, you would say that about here is the best renormalization scale for this particular SUSY point to evaluate the two-loop correction. But that's a point-by-point dependent thing. We can't really do effectively do a minimization, and whether that minimization really is accurate to four-loop order is uncertain. So there's a lot of dependence on a renormalization scheme in these. You basically have to choose a renormalization scale. We throughout use the stop mass scale. This is basically because we have very heavy stops. It doesn't really make sense. We concluded to talk about lower renormalization scales than the stop mass for what we're doing. And this is very different between different modes. So for instance, fine Higgs, if you were to use fine Higgs even for very heavy stops, it uses m top as the renormalization scale. And we saw some very odd behavior around m top for very heavy stop masses. Okay, so given all of that, all of that technical input, what does the Higgs mass look like at the three-loop order, or at least with our three-loop corrections? Well, the first thing to note that our two-loop determination through H3M is actually a little lower than we expected. It's at about 5 TeV. MH equals 125 at about 5 TeV and stop. And then the through-loop contribution increases the Higgs mass by about 0.5 to 3 GeV, and that gets you down to about m stop of 3.5 TeV. These bands are the parametric uncertainty, so that's what you would really quote as the real uncertainty in the Higgs mass in most cases. That's what is the uncertainty from just m top and alpha s being uncertain values, and those are these bands. They're about 1 to 1.5 GeV, up to about 2 GeV at 10 TeV m stop. And they're of course not equal. The
Where
top
did you get that m top? That's pretty old. And the uncertainties are much better than that.
I think this
Is that just an LHC number? Is that why?
No, I think this was yeah, I think we were worried about some of these claims that the real top mass should not be taken from these pole mass calculations, but the running mass calculations. So this might not actually be.
I mean, it's less than a GeV now.
Well, yeah, you're right. I think we ended up taking the larger uncertainty from the running mass calculation. I think that's where this comes from. You're right. This isn't. It's about 0.8 GeV, right? Uncertainty. I'll have to look back. I think that was the issue behind it. I don't actually remember. I apologize.
Does that have a big impact on your width?
Yeah, that will reduce the width by about I don't think quite a factor of 2, but it will reduce the width by something like a factor of 2, between root 2 and 2. But I think that
All right, so it's a definitional.
yeah, it's a definitional thing. I forget exactly what it's going to do.
That smaller error, does it have the other parameters materialized over? You have the more combined region space, the size can shrink because you allow the other parameters to just go off a little bit. Well, this constraint is probably a combined top mass and Higgs.
Right, the question is which is the driving term. If it's the alpha S, then it won't matter.
Well, I mean, if you fix the other parameters, you get smaller constraint on one of them. If you allow the other ones to vary, then you get larger uncertainties. And so maybe there might be a difference about how they do analysis. That's just what I want to say.
Yeah, it ultimately won't have a huge impact on the ultimate quoted uncertainty because the quoted uncertainty will be in terms of and I'll show that at the very end. The quoted uncertainty is in terms of this plus the uncertainty in difference between the 3 and 2 loop contributions from the scale uncertainty, basically. So that will only reduce a little bit if you take a smaller uncertainty on top. Yeah. Okay, and I should also note that there's a possible partial cancellation by order alpha t squared alpha s terms. That's the other leading order contribution in leading log. In just the leading log calculation, but that's unclear. And sorry, it's negative whenever the order alpha s squared alpha t contribution is positive. But that's unclear at this point. The leading log contribution is only about, I believe, 20% of the full contribution, at least in the parameter space that it's been studied. That Martin looked at it, and really it would require. Philip said it would require another PhD thesis to calculate all of these terms and include it. So there's a possible cancellation, but it's certainly, even through the leading log analysis, it doesn't look like it would be more than half the 3-loop contribution. So there's a possibility for a somewhat of a reduced 3-loop contribution there. Okay, so now let's look at how it compares with the other 2-loop codes. Well, it compares fairly well with soft SUSY, fine Higgs, and suspect, below m stop of 4 TeV. By that I mean if you take scale uncertainty bounds of about a factor of 2 in scale variation, it's fairly close. So you see just down here, this orange line, black line, and purple line, all within the scale and uncertainty bounds for the 2-loop result. Spino is off, but that's expected because it has a hard-coded, very hard to change renormalization scale. So we couldn't change the renormalization scale at the same time. So in some sense, you can see what happens with the Spino line versus what happens with all these other lines is really an effect of having a different renormalization scale. And it's a very profound difference. And having a renormalization scale fixed at a very small value rather than having it track with m stop.
Excuse me. Can I understand in a way? So for example, the other programs, if I turn up their renormalization scale or not scale, they can eventually agree with your curve?
No, so the issue with the other programs versus H3M is that we use a higher order parameters in the 2-loop calculation as well because it's hard to take that out. So this is formally higher order in some terms than these results. Because this is the 2-loop result that is fed into fine Higgs, and then the 3-loop contributions are added on. So here you can say, even if you are a little bit uncertain about the H3M 2-loop result because you're uncertain how the higher order parameters are treated, here's the contribution of the 3-loop. So you can sort of see the breakdown of what the different contributions are. Yeah. So that's because 4-loop alpha S, 4-loop MT calculations were used to feed into this 2-loop result from findings. Okay, and the divergence at large m stop is, yeah. Okay, so with all of that, and taking all of those caveats into account, what does it look like if we just try to go and look at the phenomenology of it? Well, the 3-loop contributions have a profound effect on the preferred parameter space. Remember the MH of 125 GB line was up here before. It's down to around here now. So it shifts profoundly when looking at the 3-loop contributions. And when we look at a combined error estimate, so even if the parametric error is reduced by half, say by reducing the MT uncertainty, you still have a fairly meaningful perturbative uncertainty. And the really interesting thing is you're moving the preferred M naught down even to maybe 1 TeV, 2 TeV for a accessible possibly at the LHC 3000 inverse femtobar level. So this is just some estimate of the projections for LHC at 3000 inverse femtobars. It may actually be able to probe the low M naught region of this of the 125 GeV Higgs mass at A equals 0. So that's something that you would never be able to do with the 2-loop result. And then you can also probe some of the focus point up here. there the M Gallinos is as low as 2 TeV, so that would be fairly easy to see at LHC 13. You can also say, okay, well, what about mixing? I mean, we can always add mixing to this story. So the 3-loop results significantly enhanced for large mixing. This is probably mainly due to the same enhancement at 2-loop, to the point where the 3-loop at 500 GeV is above the 125 GeV Higgs contour. So it's completely beyond just for even very low step masses. And all this isn't terribly important. I should note that the maximal contribution happens at a somewhat reduced value of the mixing mass, but it's sort of within 20% of the 2-loop result. It's still maximum around the same point. And if we look at the more popular CMSSM plane for LHC searches now, it's this A0 equals -2m0 point. And you can see this teal band is the current CMS constraint, cuts into a lot of this Higgs mass of 125 GeV line. Even up to fairly high m0, it would sort of be over here for the 2-loop. And LHC 13 would be able to cut off basically all of it, even with 100 inverse femtoflux. So if you start going to these high mixing scenarios, you'll be able to see it at A equals -2m0 with the LHC. So there's a lot of possibility for the LHC to see the 125 GeV Higgs, and it's improved by the 3-loop Higgs determination. I should say that I won't be talking about this primarily because you see that there's no, the thing that you always see in these A equals 0 plots, this v² less than 0 region, just doesn't exist for large A. And in particular, it doesn't exist for A scaling with m0. So there's no dark matter. The dark matter allowed on this plot is down in this region. It's completely ruled out by CMS, or there might be a little bit of co-annihilation allowed up there, but it's completely ruled out by CMS, and there's no signal at any of the direct detection or indirect detection experiments. So I won't be talking about this primarily because you don't have any sort of dark matter possibilities in this plane. But it is very interesting for colliders that the 3-loop Higgs. There's still some possibility even with 2-loop to see it with the typical determinations, but 3-loop is worth it. Okay, so that's enough about the Higgs mass. Let me talk a little bit about focus point dark matter. And I'll be a little bit faster. Okay, so for anyone who's not intimately familiar with this, neutral dark matter in the CMSSM is a very popular topic. So I'll go over it quickly. It's primarily Beano over most of the parameter space, so everything above this line and above this line is mostly Beano, and it's overabundant. So over close to the universe, there's too much dark matter in that plane. So you have to either be down in this region or down to the left of this co-annihilation line to have to be underabundant, and you have to be along this line in order to have the right relative density thermally. And since low mass Fermi answers is favored, and there's arguments that that this co-annihilation region is pretty much ruled out or close, or will be ruled out very quickly at LHC 13, this is probably the best region to look for dark matter in the CMSSM. This is called the focus point. In the interest of time, I'll skip over most of this. But basically, fine-tuning is improved in the focus point, but a result of that is that you have a low mu term. And because you have a low mu term, Higgsinos are relatively light, below about a TeV for 1% fine-tuning, and that means that you can have thermal Higgsino-Beano mixed dark matter. And the importance of that is that the Higgsino has the correct annihilation strength to produce the thermal relative density at 1 TeV, and below 1 TeV, Beano annihilation is too weak, barring co-annihilation effects. Higgsino annihilation is too strong, so you mix them and you get the right amount of annihilation to get omega equals, the dark matter relative density equals, sorry, the theoretical determination equals the observed. And you can basically balance mu against m1 to get the right relative. Yeah. And you can see that sort of diagrammatically. These are the S-wave neutrino annihilation diagrams. There's one that goes just as Higgsinos go to Winos, and so this is allowed even for pure Higgsino dark matter. There's several that go as Higgsino and Bino annihilate to Ws or fermions or to fermions through a scalar. I'm going to ignore these because I'm looking at heavy scalar scenarios. But basically, there's some that have just Higgsinos, some that have the Higgsino and Bino, but nothing that has just Bino, unless you have both light fermions and some amount of left-right mixing. So really, that's why you have this balance of Higgsino and Bino allowed in the right belt density. And the importance of that is that when you look at neutrino scattering of nuclei, so for direct detection, both this is the spin-independent diagram through the Higgs, the spin-dependent diagram through the Z, you end up getting significant scattering cross-sections from Bino-Higgsino mixing. And again, I'm ignoring heavy squarks. Here, it's fairly obvious you need some Bino and some Higgsino in order to have any scattering. If you have just Binos, there's no scattering. If you have just Higgsinos, there's no scattering. Here, it looks as if you can get scattering just with Higgsinos, but in fact, if you have no Bino mixing, then the Higgsino up contribution cancels the Higgsino down contribution. So you need some amount of mixing in order to split those contributions and get some amount of scattering through the Z. Or if you drive the Bino mass up to above about 10 to the 13 GeV, if you have just pure Higgsinos, truly pure Higgsinos, then you end up getting scattering through the Z. You have Dirac Higgsinos scattering through the Z. That's ruled out ages ago. So that's not even something that we think about anymore. So to look at this and look at what these constraints look like in the focus point for thermal dark matter, we're looking at the focus point with fixed omega chi equals omega dark matter. This is kind of an odd parameter space. Basically what we're saying is take this old M1/2 versus M0 plane and map the thermal line onto a particular line for tan beta. So tan beta 10 is here, and we've mapped the thermal line just onto this line, and so tan beta 15, tan beta 20, all points in this parameter space have M0 set to produce the right belt density. So this is just the very thermal, very exactly thermal scenario for the focus point. It's only a thin slice, and it allows us to look at the tan beta dependence, which is important in some cases. And you also have A, which is the other parameter in the same SSM. Focus point requires A much less than M0, so we just set it to 0. So we ignore that. And you can see here's the required value of M0. It varies with tan beta. At the low end, it's maybe 3 up to 8 TeV. So large values of M0, and it gets larger as you go down to tan beta 10, and even larger as you go to tan beta 5, say. And then the correct Higgs mass at 2 loop is somewhere around here. So what does that say for various prospects for dark matter direct detection? Well, various prospects for dark matter detection. Well, if we look at spin-independent direct detection, this is sigma SI with Xenon 100, and this is almost certainly the last time I will ever show this slide because Flux will be coming out with data soon. Here are the exclusion contours. It's very strong for mu greater than 0, significantly weaker for mu less than 0. And basically, the reason that it's so much stronger for mu greater than 0 is because you have an additive effect between the Higgsino up and Higgsino down contributions to the Higgs coupling. Here you have a canceling effect. And in fact, for a particular value of tan beta, which is actually below this plot, you will actually, for these parameters, you will get a complete cancellation. You will have no Higgs coupling. But in general, you have limits up to about M1/2 of 1.8 TeV. Here, the CMS bound at 5 inverse femtobarns at least is around 500 GeV for M1/2. So it's much stronger in CMS, even if you have a somewhat subdominant relative density from Xenon 100. For mu greater than 0. For mu less than 0, you have somewhat smaller, somewhat weaker bounds, but it's still fairly strong. And you can see there's a very very weak dependence upon M1/2. So Lux even will probably constrain much of this parameter space, and Xenon 100 will blow it out of the water. So this entire parameter space up to where it becomes basically pure Higgs Xenon up here, and everything but this small area down here where you have basically zero coupling because of odd effects with the pseudoscalar Higgs, and because it's the CMSSM. Basically, these entire plots will be blown up. And this is just a numerical effect. It's an issue in it's a known issue in soft SUSY. There's no reason we shouldn't be able to get beyond here. Now, there's some uncertainty in this determination, and this is also probably one of the last times I'll show this slide because it's starting to become less uncertain. People are coalescing, but there's a traditional uncertainty in the strange quark content of the nucleon. Basically, the amount of the mass of the nucleon that is contributed by the strange quark. Traditionally, the value is about 36%, and this is a determination from chiral perturbation theory. And really, it's an experimental result because all the it was some input from meson scattering input. So really, it's a chiral perturbation theory determination because all the stuff about the strange quark comes from chiral perturbation theory. And then this, the meson scattering data input is about the UU bar and DQ bar contributions. Whereas a more recent calculation says it's more like 5%. So these are two very different values. And because what we're talking about is the Higgs coupling, and the Higgs doesn't couple to gluons, this is, there's a very big difference in the Higgs coupling. Enough to produce about a factor of 3 difference between the Higgs coupling, a factor of √3 difference in the Higgs couplings, a factor of about 3 difference in the cross section between the lattice determination and the chiral perturbation theory determination. However, the community is starting to coalesce on the lower value. Non-perturbative effects seem to make the chiral perturbation theory result more consistent. And as evidence that the theory is coalescing, Micromegas at least has adopted the smaller value. Micromegas is one of the big codes. I don't think Dark SUSY has yet, but I've heard that they're thinking about it. So probably this is the value that is more reasonable. It's the one that I use, and it's conservative because if you have this value, then your bounds are even stronger. Okay, that was spin independent. Spin dependent is weaker. You just have lower cross sections relative to what can be seen. But Cruise 60, after 1 year of sensitivity, might have some ability to probe it up to about 1.3 TeV. You have solar muon flux, just from stuff from neutralinos annihilating the sun. Has some ability to probe this region. This is the current IceCube plus D core, about 1 year of data line. It's actually significantly weaker than they were predicting. They were predicting something up here, but it's a significantly weaker result than they predicted. But hopefully that will improve in their experimental. This is 1 year. They'll have 10 years of data, and hopefully they'll have better discrimination ability as they work on it more. So we might even be able to get up to maybe 1.2 TeV. So IceCube will have some significant constraining power. And finally, gamma ray signals have a significant amount of ability to probe this region. Fermi isn't quite there yet. This is 5 times the Fermi sensitivity from dwarf spheroidals, and they'll only have about twice this at their final data set. But 5 times the Fermi data will be able to probe up to about 800 GeV, 20 times up to about 1.5 TeV. So there's some possibility for the next generation of gamma ray experiments. On the not quite so possible level, the Earth neutrino flux is orders and orders of magnitude below what you would need to look at IceCube plus D core. You can see it's about maybe 7 orders of magnitude weaker. So we're not seeing any neutrinos from the Earth from this. Antimatter is not so hopeful. The antiproton flux is around 3 times 10 to the negative 9 at best. The current flux from Pamela is 7.2 times 10 to the negative 8 in the same units, these grid units that they use for these sorts of things. And And really, there's no striking features. This is a very weak signal to noise, even for very light neutrinos. At the same time, antideuterons have not been seen yet, and the expected sensitivity from GAPS, which is the best next generation anti-deuteron experiment, is only about an order of magnitude weaker than what you would need to see even the lightest neutralinos. AMS is about an order of magnitude weaker sensitivity than that. So there's not really very much hope for antimatter. Okay, so finally tying things together in the last two slides. What does the Higgs mass look like at 3 loops in this plane? Well, it shifts the preferred region significantly, as I said before, down to much lower values of m1/2. So this is the preferred region here. And if we look at that in comparison to the various current and future bounds, you see that Xenon 100 excludes most of this region for mu greater than 0. I apologize, there's no greater than 0 there. And even for mu less than 0, it cuts significantly into it, whereas they don't even touch the 2-loop result, which will be somewhere up there. Ku will be able to constrain some of the region, and while neither Atlas nor Deepcore are there right now, there's some possibility for them to prove that. So hopeful things, especially if we start looking at higher order Higgs mass, maybe that makes things a lot more optimistic as far as our ability to prove it. Okay, so in conclusion, there's various motivations, as I said, to consider TV scale SUSY. I won't go over them again. There's a lot more uncertainty, even if with all the caveats that I was saying, you're a little bit uncertain about the Higgs mass that I produce. I hope that I convinced you that there's a lot of uncertainty in theory determinations, probably more than is typically quoted by each individual code itself. 3-loop contributions can raise it by several GeV. And this is a generally accepted fact. How much is uncertain? We think we have an answer, at least for some contributions, but it's generally believed that it will raise it by several GeV, especially for heavier soft masses. And there are strong prospects for discovering or ruling out focus point dark matter. Thank you.
So your comment, even for large mixing, you have large contribution. So large mixing is one stop lighter, one stop heavier. So even those cases, you have large 3-loop contribution.
Yeah.
No matter what, if you satisfy the Higgs mass, then you have large 3-loop.
Yeah, exactly, and that's, and I mean, I agree that it's there's a little bit of a I think sociological issue here of everyone who does these very careful Higgs mass contributions wants to report their own error in terms of scale uncertainty and parametric uncertainty, and it's very hard to admit that there's a lot of uncertainty in how you do everything. So that's why I always go back to that 2004 paper, because that's basically a bunch of people who had different codes got together and wrote a paper together where they didn't have to compete on their uncertainties. They could actually be honest about, well, okay, when we start doing a scatter plot of how wide the bands are when we just take all of our results, here's what they look like. So I think there's a lot more uncertainty than is usually quoted. I'm not sure how much there is, but yeah, I think that it's generally felt that this is true, and I've heard a lot of even from people who know just a little bit about this, and to people who are experts on it. I'll say that the 3-loop contributions really should raise the Higgs mass. So there's a general effect. How big it should be is uncertain, but in all the talk about when we put out this paper and various talks were given on it, no one that I know of has said, well, the 3-loop contributions should actually be negative. This is sort of, I think, a generally accepted fact that it should be somewhat higher.
So I wonder what 4-loop contribution would probably raise it, even by 1 GeV or 2 GeV raised by 4-loop contribution.
Yeah. I mean that's. I think that in some sense, it's probably. So here's the parametric uncertainty. It might be down by a factor of 2, but the parametric uncertainty is fairly high. versus, well, okay, so the parametric uncertainty here might be more like 1.5 GeV, just looking at the right scale here, 1.5 GeV, maybe down to 1 GeV. Whereas the perturbative uncertainty is maybe 3 GeV, is maybe a GeV and a half from the difference between the 3-loop and 2-loop. I think that 4-loop might be a little bit higher, but the difference is likely to be within sort of the parametric and perturbative uncertainty combined between the 3-loop and 2-loop. So in some sense, yes, we expect it to be a little bit higher, but it's probably closer to within the honest uncertainty that are quoted by each individual code, as opposed to this is big uncertainty. No one quotes 3 GeV uncertainty in their individual results.
Can you go back to the next to last plot, or the next to last page? Yeah. So, if I'm understanding this correctly, the blue and the green are your favored regions.
Yes.
The overlaid sort of red things are excluded.
This is excluded by Xenon 100. This is at mu less than 0. This is excluded by Xenon 100 at mu greater than 0. So that's a really different.
So in some sense, your central value
Is around there.
is excluded.
For
Except
some.
for mu greater than 0 is completely excluded, except for tan beta between the sliver of
Yeah.
52 and 54.
Yeah, and this is completely a CMSSM result. If we took out, this is because of behavior of the pseudoscalar and how it feeds into the developed density. So if we go beyond the CMSSM, this is, well, if you go beyond the CMSSM, then where the Higgs is uncertain. So yeah, but yeah, that's correct. Sorry.
I mean, if I were to take this very seriously, and I'm not sure that this is a very tight constraint on everything other than on tan beta.
Yeah, I believe that's true. Well,
I mean, again, it depends on your model, but one is
He's using CMSSM.
what?
He's using CMSSM.
yeah, I'm using
Yeah,
CMSSM.
Yeah, I know, but
So
but it's either. I mean, in some sense, you're saying either it's there, or this is just wrong,
Yeah.
or the CSMSM is just wrong.
Yeah, it's cool.
Yeah, and that's certainly possible. I think that, again, I think that probably these bands should be a little bit wider.
Which
being
band?
on the Higgs mass bands. Again, this
Be
is.
that as it may, I mean, in some sense, what's really driving that is the width of the Xenon 100 result, and the constraints of whether you pick mu greater than 0 or less than 0.
Oh yeah, and I agree. Like maybe even Lux and certainly Xenon 110 will completely kill this. Xenon 110 will probably be up to somewhere.
What about for mu less than 0?
It should be.
Should it
It's
fill out
hard
the
to
rest
say
of the
because
space?
it will go into there. This is a stupid numerical thing that we were never able to solve, but it should
But if
be.
I'm reading you correctly, it sounds like what you're saying is that the CMSSM is about to completely be excluded. Am I reading
no.
it right?
Oh, okay. The CMSSM, the focus point region of the CMSSM at completely thermal is about to be excluded, or we'll see something. Now, it's very easy to avoid that, even with thermal dark matter, by going a little bit. Where is it? Okay, by going from here on this line, going over just a little bit into here. Now your relic density is maybe 10% of the observed relic density. So you're weakening the Xenon 100 bounds significantly.
Okay, and how do you put in the CDMS excess in silicon?
That's not on this.
That's a
slide.
small dark matter mass, but here dark matter mass is
Yeah, here dark matter
So
mass
here
is-
you're just assuming, I mean, in some sense you've pretended that is just wrong.
Well, you
Or
basically
that's just
can't-
not dark matter.
There are a couple of models that vary, that try to fit neutralinos to that, but that's basically impossible.
So in other words, if that data is real, we are so far off in our understanding of Susie.
No.
Well,
But
if
then
that data, well, okay,
yes.
one scenario that you could have is you could have neutralinos with 10% of the relic density, and have some other thing at about 10 GeV with 90% of the relic density. If that situation is real, then using dark matter to probe Susie, or at least to probe
So you'd
CMS
need
and
another
like scenarios.
conservation law.
Huh?
You'd need something else conserved, so you'd have two dark matter candidates.
Yeah, that's true. And also,
But then you'd have a
using dark
very
matter
different
to talk
Susie.
about this would be very hard.
No. You build another model, not see like within MSSM you can come up with different kinds of models, like or extend the MSSM.
You'd have to extend it. There need to be some
Exactly.
other particle that's going to be the dark matter particle, and there would need to be some other conservation law that's protecting its lifetime.
Whatever.
Yeah, or you don't necessarily even have to have that. You can just say that neutralinos are dark matter, so none of the dark matter constraints even apply on this plane.
Right, but that,
Yeah.
right, so in other words, Susie might be correct, it just has nothing to do with dark matter.
Yeah. Or at least the MSSM has.
MSSM. Maybe MSSM is not correct. Yes.
Or it may be correct, it just doesn't have anything to do with dark matter, right? It may be giving us 100 GeV extra thing, but the
So
dark
there
matter
are
is axions or
Many
something.
model building options.
Yeah.
So,
Okay.
So a long time back, I remember that we used to see these poles for mu less than 0, like where you really cancel these dark matter direct detection cross section. I thought that you still can do it in the focus point.
Oh yeah. It's below the. It is below the spot.
Okay. So that means you know what I mean. Like direct detection cross section could be 0, but mu has a different sign, so that direct. So really, you don't see much, see at all, anything at all in any of the direct detection experiments because it gets cancelled out. But
Yeah, that exists, and that's what's happening as these lines are as these contours are curving up.
Okay.
So it happens, I think, for tan beta 3 or something.
Something like
Yeah, it's just not on this plot because of what we decided to plot. I don't. Oh well, I'll say not just because of what we decided to plot. It doesn't happen down to 5, and below 5 you start running into big issues. That said, as you go down here and try to fit the relic density, fit to the relic density in the CM at least, because that's what we're talking about, the Higgs mass starts going kind of odd. So you have to start worrying about Higgs mass as well then.
Question for you?
So did you talk to Karen and Wagner by any chance about the 6 3-loop contribution? Usually they always come up with some arguments of this.
We had an email correspondence, and I'm trying to. I'll have to go back.
So it looks very exciting because
Yeah.
now it's a 3 GeV difference means a lot.
Yeah, and I will admit that there's still some uncertainties in it, but
Yeah, but still.
but it's a really important result. Just to get out there to even making this statement, there's a lot of uncertainties in these results is important because I've talked to people who basically say find Higgs spits out a value, I'll tack on a half a GeV uncertainty. That's word of God. So, and that really is, that's definitely not true.
Okay, I think that we can.